Okay, we're going to use induction to create a conjecture in this example. So, what conjecture can be made about the number of dots in the nth term of this geometric pattern? So this one's kind of cool. We actually get a visual to work with. So the nth term means here's our first term, second term, third term, fourth term. So could we figure out how many dots are in the fifth term or the 10th term or the 100th term of this geometric pattern? So we want to look to see what we notice about these dots and what patterns might emerge. And then we can use inductive reasoning based on the pattern we see to make a conjecture about the nth term. Okay, so a couple things you might notice is we have, in our first term, we have 2 dots. In our second term, we have 6 dots, and we have 3. Third term, we have 12, and fourth, we have 8. So a number of dots is increasing. It's not increasing by the same amount. We went from 2 to 6 to 12 to 20. Because we actually have a visual on this one, I think it's helpful to notice patterns here. Well, we have rows. Like term 1 has 1 row, term 2 has 2 rows, term 3 has 3 rows, term 4 has 4 rows. I can predict that term 5 will have 5 rows. 1, 1, 2, ooh, that's not very straight. 1, 2, 3, 4, 5. How many columns do we notice? Well, term 1 had 2 columns. Term 2 had 3 columns. Term 3 had 1, 2, 3, 4 columns. Term 4 had 1, 2, 3, 4, 5 columns. So our number of columns is increasing by 1. So if we just had 1, 2, 3, 4, 5 columns, I think we'll have 6 columns in term 5. Let me go ahead and draw that in, and then we'll talk about another thing we noticed. So 6 columns, we've got 1 column in. Here's 2, 3, 4, 5, 6. And then we can fill in all of our dots, like so. Okay, how many total dots do we have here? Well, we can quickly just multiply. We have 5 by 6, so we have 30 dots. And you notice we found that by multiplying, right? We did kind of the length times the width. So let's focus on that a little bit. Our length is whatever term we have. Term 1 had 1 for the length. Term 2 had 2 for the length. Term 3 had 3 for the length. So whatever term we're on, it says, and we were asked to find the number of dots in the nth term. So whatever term we're on, that's how many dots there are in the length. How many dots are there? I'm going to kind of put this above in the width. Well, if there are 5 dots in the length, we said there was 1 more in the width. 1, 2, 3, 4, 5 plus 1. So if our number of dots in the length was n, then we can add 1 to it to find n plus 1. So let's just see if that makes sense. If we're in the 4th term, that means that n equals 4. So are we taking 4 times 4 plus 1, which is 5. 4 times 5 is 20. So this pattern is working, or what we have set up so far seems to make sense. So the total number of dots can be found by multiplying our length times our width. I'm going to write the n first, n times n plus 1. So that's a conjecture we're making. That will give us the number of dots in the nth term of this geometric pattern. We also could represent that with, if we were to multiply it out, n times n is n squared, plus n times 1 is n. So both of those are the same statement, just one is multiplied out, one is showing more of a length times a width idea. But that's our conjecture on how to find the number of dots in the nth term of the geometric pattern.